In a vacuum, molecules react at any point throughout the region, even remote regions, allowing a more uniform deposition. If the temperature is just right, the reactant bonds break as they reach the wafer's surface. The energized molecular fragments, seeking stability, nucleate as the silicon nitride layer. As gases entering the furnace begin to react, their concentrations decrease along the length of the tube. Slightly increasing the temperature near the outlet increases the reaction rate and ensures all wafers have a uniform thickness. In addition to being a good insulator, silicon nitride is very dense and resists the diffusion of other materials. It is an excellent barrier to oxygen and water vapor. After patterning the wafers with photoresist and a mask, the nitride not covered by photoresist is etched. The transistors will be built in the regions still protected by silicon nitride. In an oxidation furnace, a thick insulating layer of silicon dioxide, known as field oxide, will be grown where the nitride has been etched. Once again, oxygen combined with hydrogen is introduced on the wafers as steam. During the initial phases of oxidation, the oxide thickness is directly related to the oxidation time. This changes as the oxidation layer grows thicker. Oxygen finds it difficult to migrate through the growing oxide to reach the more loosely bonded silicon atoms in the substrate. This reduces the concentration of oxidant on the surface and slows the process. Although oxidants are not able to migrate through the silicon nitride, some diffuse beneath the original nitride layer. This creates a transition region between the original thin oxide and thick field oxide and provides a gentler slope for the remaining depositions. This thick oxide reduces the electric fields between the surface and underlying regions and prevents unwanted leakage of current. After the remaining nitride layer is removed, the wafers are implanted with boron ions. The thin oxide layer, damaged by ion implantation, is removed, and a new layer of silicon dioxide is grown in the gate area. The first conductive layer to be deposited is doped polysilicon, which will become the gate electrodes of our CMOS transistors. Certain electrical properties are important for a good conducting film. They include a low resistance to the flow of current, a low resistance between conductive layers so contact holes can be small, and a high resistance to electromigration. This SEM shows the voids and hillocks created by electromigration when atoms migrate as a result of the wind from flowing current. Polysilicon is deposited in a low-pressure CVD process. The gaseous source of silicon to be introduced is usually silane, diluted by a nitrogen carrier gas in a low-pressure furnace at approximately 620 degrees Celsius. When silicon is deposited on an oxide surface, it consists of random orientations of many single crystal granules. To make polysilicon more conductive, it is heavily doped either from within the furnace or by ion implantation with phosphorus or arsenic. The N-type dopant is captured along the boundaries and incorporated into the silicon crystals. This makes polysilicon a reasonably good conductor that can withstand high temperatures and is resistant to chemicals normally used in cleaning operations. After etching, the polysilicon layer becomes the gate electrodes that turn the transistors on and off. As conductive materials are shaped, they present a challenge for the insulating materials that must surround them, such as corner pockets that are difficult to fill, high vertical sidewalls that might result in thinner deposition, and sharp jutting edges that might pierce the oxide and cause a short circuit. In a self-aligned gate process, the side edges of the gate become the masking edge for the implantation of the drain and source regions. In some of today's densely packed, more complex chips, the channel lengths of MOS transistors have been shortened to increase the speed at which transistors turn on and off. This causes electric fields, particularly around the drain area, to become so large they create reliability problems. One way to reduce this problem is to place a lightly doped region in the drain area closest to the gate. First, a uniform lightly doped region is created through ion implantation. Then, a conformal oxide film is deposited. Previous oxides have been deposited at high temperatures. Now, however, to avoid diffusion of dopants already in the silicon, the moderate temperatures of low-pressure CVD are preferred. To ensure the film has a uniform thickness that follows the contours of the surface, TIOS is selected as the silicon source. Behind this system, we see a CVD cluster tool with 4 separate reactors. Inside each reactor,